Hi, my name is John Paul Raj, and my mission in life is to make the learning of math fun. So if you're new to this channel, please do consider subscribing. On this video, we're considering the different cases when a limit of a function does not exist. On an earlier video, we had already seen that when the left-hand limit is not equal to the right-hand limit, we say that the limit of a function does not exist. But there are two other cases when we can say that the limit of a function does not exist. One of them is quite obvious. The other one might not be so obvious. Let's find out why. Previously, we've already seen the case when the left-hand limit is not equal to the right-hand limit, and so we said that the limit of the function is not defined. I'll link that video in the description below, so if you haven't already seen it, you must take a look at it. The second case is when we have the limit as x approaches a number, a value, the limit of that function is becoming too large. So we don't say equal to infinity, but we say becomes too large. Okay, so in that case, we say that the limit does not exist. Let's take a look at the definition first and then come back to this idea again, all right? So in the definition, when we saw the definition, we said that the limit is the y value, the y value. That clearly means it's a definite finite value, the y value. That word the also suggests that from both the left and the right hand value can't be different, it has to be one. It's a definite article the. So when you say the, it means one value from both the left hand side and the right hand side, and it must be a certain finite y value. It can't become large and large and large and increase up to infinity. And that condition that I wrote there, the second condition, that when you have the limit of a function becoming too large, becoming so large that it increases up to infinity, can be positive or negative, very large positive value or very large negative value, all right? As x approaches a finite value like a, if the value of the function becomes too large, we say that the limit does not exist. Let's illustrate this with an example. So our example is the function f of x is equal to 1 over x, and we're considering the limit, the behavior of the function as x approaches 0, all right? X approaches 0 is not becoming 0, it's approaching. So we're looking at the behavior as x approaches 0 from both sides. So let me just quickly draw the graph, and that's 0. I hope you can see this. This is 0. So you're looking at the behavior of this function as x approaches from the right-hand side, as x approaches 0 from the left-hand side, from both sides, what's happening to this function. And we know from the graph of 1 over x, okay, the reciprocal function, that it's a graph like this, okay? It's a graph like that. So what can we say? So then as we approach 0 from the right-hand side, the values, the corresponding values, y values, the function values are becoming large positive values, okay? You can see that. That's the asymptotic behavior we were talking about. And the same thing happens that when you look at values of x approaching 0, from the left-hand side, the function values, the y values becoming small, negative, more negative, and it's becoming a large negative number. In other words, a very small number. So from the right-hand side, as x approaches 0 from the right-hand side, the function values go towards positive infinity, and as x approaches 0 from the left-hand side, the function value is going towards negative infinity. As such, we say that the limit is not a finite value. Technically, it's not right to say that the limit becomes infinity or the limit is equal to infinity, because the word limit means that it's a finite value. You cannot have an infinite limit. So we say that the limit does not exist. Okay, so it's the same case as the vertical asymptote. Okay, for those of you who haven't seen my video on vertical asymptote, I'll link that in the description below. Take a look at it. But looking at vertical asymptotes through the lens of limits gives the idea that the limit does not exist at that value where we have a vertical asymptote. Okay, in the same way, if you were to generalize any function with that denominator having a problem, vertical asymptote, and we consider the limit approaching that value, the lens, using the lens of limits to understand vertical asymptotes. So basically what's happening, we say that the limit does not exist. Don't even write equal to infinity, okay? So technically it's not correct. So we just say that the limit does not exist. So whenever you have a function Whenever you have a function where the denominator becomes 0, the limit as x approaches that value where you have the denominator becoming 0, it will have the same asymptotic, the vertical asymptotic behavior. So this is the second case where the function has a vertical asymptote. We say that the limit does not exist. The function becomes either too large positive infinity or tends towards negative infinity. Basically, we say that through the lens of limits, the limit of the function does not exist at that value where you actually have a vertical asymptote. And the third case where the limit does not exist is not so obvious. So I want you to pay attention very carefully, all right? The example we're going to look at is this function f of x is equal to sine of 1 over x. And we're looking at the limit, the behavior of the function as x approaches 0, the behavior of sine of 1 over x as x approaches 0. The behavior can be described as an oscillating behavior. Oscillating behavior, meaning it goes, fluctuates, all right? So let's first look at the graph of this function quickly. Sine of 1 over x, right? So I'm just going to put in sine 1 over x. And I'm just going to change this to radians, okay? Oh, I need to enter this again. Cool, no problem. Sine and 1 over x. 1 over x. Here we go. And let's look at the graph. And when you look at the graph, this is the function 1 over x. You look at the graph and we're looking at the behavior of the graph around 0, right, left-hand side, right-hand side. It's not so obvious, right? It's not so, and that's why I said it's not so obvious. And as I try to zoom in, you can see that it's oscillating. But it's still not obvious, I would say. At least I didn't find it so obvious. I thought that it's approaching 0 from the right-hand side and it's approaching 0 despite the oscillations. I'm going to insert a calculator page, all right? This is a CAS calculator, so I can do all these fun explorations. I'm going to insert the template for the limit, which is here. And we want x approaching 0 from the right-hand side, left-hand side. Okay, so I'm just going to say plus. That means values of x approaching from the right-hand side. We've already defined the function on the graph page, so I can just enter f1 of x and I'm going to hit enter. Watch. Undefined. So even graphically, when you see that the graph kind of seems to approach 0, you can verify it using the CAS calculator that that's not true, which is why I said it's not so obvious. And if I do the same thing, and I try and see what's happening to the limit as x approaches 0 from the left-hand side, okay, so I'm going to hit 0 minus, hit enter, undefined. So the limit is undefined apparently from both ends, the right side of 0 and as x approaches 0 from the left-hand side, undefined. And it's not clear, it's not so obvious using the graph, and which is why I said it is not so obvious. So how do we explain this? Let me try and make it as simple as I can. And here I have this little table, okay? And I'll try and make it as, here we go. Now it's clear to everyone. I'll try and make this as simple as I can. What's happening is this. We are looking at values of x values approaching 0. But the sign of the value that we are considering is 1 over x. I think that's where, it becomes a little not so obvious, okay? So the x values are approaching 0, but the sign of the value that you're considering, the domain for that sine function is 1 over x. It's not x, it's a reciprocal of x. To illustrate that, I made this table. And so we are looking at what's going to happen at around x is equal to 0, the behavior of the function sine of 1 over x at around x equal to 0, both from the right-hand side and the left-hand side. This is the example of right-hand side. You can do the same thing for the left-hand side. So what I've done is that this is a safe enough distance, 0.1, okay? 0.1 on the right-hand side of 0. And 0.1 is like 1 over 10, right? 0.01 is, 0.01 is 1 over 100. And 0.001 is 1 over 1000. And those values are becoming smaller and smaller as they're approaching 0 from the right-hand side of 0, correct? So I'll just make a mention of that. This is x approaching 0 from the right-hand side. Cool? Now, what will happen to 1 over x? Watch. When x is 0.1, 1 over x is 10. When x is 0.01, 1 over x happens to be 100. When x is 0.001, 1 over x happens to be 1000. What does that mean? Okay, now watch. Between 10 and 100, there are like 90 steps. If you were to, break it down that way, there are like 90 steps between 10 and 100. And we're looking at sine of these values. Sine of these values. In the radians mode, sine of 2 pi, you'll have one complete sine wave, right? 2 pi is like 6.28. And approximately 90 steps would mean you'll have about 14 sine waves. 14 sine waves. Just in that region, okay? Just in this region, we're going to have 14 different sine waves, okay? Now, what's going to happen when we come to the next block? That means between 100 and 1000. Between 100 and 1000, that's like almost 143. I worked it out, okay? So almost like 143 sine waves. Because you've got a gap of how many? How much there? This is 90. Already the gap has now gone up to 900, right? Okay, so if you divide 900 by 6.28, something like that, you'll get about 143 sine waves. So basically what's happening is that it's not that the sine wave, because the sine wave is an oscillating wave, but the oscillations are increasing rapidly. It's not at the same rate, it's increasing rapidly. So as x values become smaller and smaller, 1 over x becomes larger and larger, and consequently, sine of 1 over x is producing many more sine waves. If there were 14 sine waves from between 0.1 and 0.01, x values, x values 0.1 and if there are 14 complete sine waves, imagine what's happening in that interval. Imagine what's going to happen in intervals much closer to 0. It's going to increase. So sine is an oscillating function anyway, but the oscillations become so rapid because the number of waves are increasing. And that is why when you look at the graph of sine of 1 over x, as x approaches 0 from the right hand side, you see the oscillations. But as we sort using this numerical approach, that the number of sine waves, the frequency of sine waves, initially it's not as much, but as it comes closer and closer, the frequency of sine waves increase. And so the fluctuations become so rapid that when you're approaching x from the right hand side, and the same behavior is even from the left hand side, the limit of the function basically is not defined because it's oscillating. It's not becoming infinite as we saw in the earlier case, it's oscillating. And because of that oscillating behavior, we say that the limit of the function does not exist. So the third case when a function does not have a limit is when it has an oscillating behavior like sine of 1 over x around x is equal to 0. So we saw 3 cases when we said that the function does not have a limit. First, when the left-hand limit is not equal to the right-hand limit. Second, when the function has a vertical asymptote. At point where it has a vertical asymptote, the value of the function becomes too large, becoming positive infinity or negative infinity. Don't say that the limit becomes infinite. Just say that the limit does not exist at that value where you have a vertical asymptote. And the third case is when the function has an oscillating behavior like sine of 1 over x as x approaches 0. I'm going to see you in the next video.